out. So all of this is a cycle going around and around. And when this cycle goes around, okay, that's where energy consumption happens. Okay. Now, but the main consumption is how to produce the 6 degrees that goes into the coil. The fan is just very minute as compared to how to produce the 6 degrees Celsius, which later on I will discuss to you. Okay. So components to produce coldness or hotness is basically following the cycle. Okay. So evaporator earlier, as I was mentioning, as I was discussing to you, is basically that's where this is where the coil is, okay, and and this is where it has a heat exchange with the refrigerant, and the refrigerant is moves into the compressor, wherein pressure where it's gonna be sucked into this from. So the pressure will be from a low pressure going to be going to a high pressure, and that pressure will go into the condenser to reduce some heat, and it goes to an expansion device so that the pressure will be lower and produce cooling. So it just goes here round and round. Okay, so just for everybody, and I'm sure some of you guys know already what these parts are. A compressor looks like this. Okay, so this usually for direct expansion units is usually located at the outer units. So this is the heart of the air conditioning, because this is the one driving the refrigerant around the cycle. Okay, and we also have the expansion valve on the other side. So if this one is producing high pressure, this one is decreasing the pressure by expanding by expanding the pathway of the refrigerant, thus producing coolness. Okay, and there's also the evaporator here. So the evaporator is where we produce the heat exchange between the room, between the air before the coil, and cools it down to after the coil based on the in and out temperatures of the refrigerant, or for chilled waters, the chilled water coming in and out here. And the condenser is the one that's rejecting the air to the atmosphere. So it's outside for direct expansion units, and for chilled water units, it's heat transferred to a cooling tower, so that the cooling tower will be the one that's gonna reject the air out to the atmosphere. Okay. So as I've mentioned earlier, these are the types of air conditioning. So to the left are the split types, even the multi-split or VRVs, and to the right is the chilled water system. Okay, so again, this is also a play of heat transfer. So if we're gonna compare the two, you're gonna see that direct expansion, by the word itself, direct, you're getting your cooling from the refrigerant itself, okay, and then blown into the area where you want to cool. Okay, as compared to the chilled water system, the cycle is still the same, but there are two levels of a heat exchange. One is from the chiller to an evaporator, wherein the evaporator has a water going through it, and that's the thing that's bringing down the temperature to 6 degrees, and that water is being pumped into the building, distributing it to all of the FCUs. Okay, and then the condensing side, we have the cooling towers outside. Okay, so there's also a cooling water pump going to the condensers in order to complete the cycle. Now that's for the water cooled chiller, but there's another type, which is the air cooled chiller, and the air cooled chiller is just basically directing the heat exchange to air as compared to the other one, which is using water. Okay. Now there are benefits for either the chilled water or the air cooled chiller or the water cooled chiller. There are benefits and pros and cons for both of them, which I will be discussing it later on. Okay. Okay. Now, let me discuss the vapor compression cycle, because this is the basic concept that's being that I was talking to you about. If you understand this, it's basically gives you more power to be able to do your energy audits down the line. Okay. Now, let me compare it. Let me discuss this to you the way I discussed about the FCU earlier. Okay. So, as I was describing to you earlier, for example, in the evaporator, and this is where earlier I've mentioned that it's going through the return air wheel at 23 degrees Celsius. Okay. So the 23 degrees Celsius interacts with the refrigerant through the cooling coils of the evaporator. Okay. And in the evaporator, the refrigerant is colder than the surroundings. Heat is absorbed and the liquid starts to evaporate and become a vapor. And this refrigerant vapor will go to a compressor. Okay. So approximately the refrigerant here will be maybe around 15 degrees Celsius, low pressure, low temperature. And this will be compressed to a hot gas at around 70 degrees Celsius. Okay. And of course, this is high pressure and high temperature. But before we go to the other side, we need to cool it, but we have to maintain the pressure. Okay. So we let this refrigerant pass through a condenser, and the air is discharged at approximately 45 degrees Celsius. Okay, these are all approximations only, just for you to visualize how the heat transfer is happening in this cycle. And then when it goes at this point, okay, so it's going to be a warm liquid at around 45 degrees Celsius, and the refrigerant is hotter than the surroundings, and the refrigerant heat is rejected and refrigerant condenses into a liquid. Okay. Now, when it goes through the expansion device, the refrigerant liquid flows through a valve to a low pressure and the temperature state, and it's going to be a cold liquid gas mixture at 6 degrees Celsius. So as you can see, after this, 6 degrees Celsius is going to enter the evaporator, and the cycle goes over and over again. So if you can, as you can see, in the vapor compression cycle, there are many the phases of the refrigerant changes from air, from vapor to liquid at various pressures and temperature. Okay, so and these values are just assumptions, but typically this can vary depending on the type of refrigerant that we are using. Okay, so and of course the pressures also vary depending on the type of refrigerant we are using, which I will also be discussing later on. Okay. Now let me discuss more in detail the direct expansion systems and how is it compared to the vapor compression cycle. Okay. Now, if you look at the typical window type, okay, so the evaporator is in here in the front side, and the condenser is at the rear. Okay, because that's where the heat is rejected to the atmosphere. So this is the profile. And the compressor and the expansion device, they're just inside, they're all piped in. And the fan is also here. Sometimes the condenser fan and the evaporator fan are just one shaft, okay? But the high-tech ones, they have individual motors for each one, so that there's going to be better controls, particularly the inverter type, window type units, okay? Now let me move into split type units. So you see, as you can see, the cycle is still the same, although the evaporator shall just be the fan coil unit, like a wall mounted unit over here, okay? Or it could be a floor mounted unit, a ceiling concealed ducted unit, a ceiling unit, or a ceiling cassette unit, but the condenser is outside, okay? But the cycle is still the same. Okay, so and the split type, at least it's more for architects, it's more aesthetic inside the room, but could be not good for them when there's too many outdoor units outside. Okay, but anyway, there's going to be a pipe separation between the condensing unit and the indoor unit, and of course there's a limit for it for the distance depending on the manufacturer. Okay, so for the installation, this needs to be surveyed so that the distance will be measured and the appropriate air conditioning unit will be recommended depending on the unit. Mind you that the farther the separation, the less efficient that the system will get. Okay. Now let's get into the chilled water system. So as you can see, the system is still the same. Okay. Although the chiller is basically the whole vapor compression cycle is already there. Okay. But the product is gonna be chilled water instead of cool air. Okay. And the chilled water is gonna be pumped into the building, okay, and distribute at 6 degrees in the whole of building, and there could be various fan coil units inside it, and then it's gonna distribute air and then absorb the air in those areas that could return to 12 degrees Celsius to the evaporator, okay, and then it's gonna be processed by the chiller itself, okay, inside, okay. Now let's talk about chilled water system. So basically, it's still the same vapor compression cycle, but the evaporator is like I mentioned to you before earlier. But the condenser also now has a pump going to a cooling tower, and it will be cooled in the tower and then return again to the condenser, and then the chiller will also operate in its own cycle, and the evaporator will also operate in its own cycle. So all of this will be working as a system to produce the cooling for the building, or like a mall or a hotel, and there will be controls to be able to efficiently operate all of this. Okay. Right. Now, as I've mentioned, chilled water system uses cooling towers. Okay. And the reason why I want to focus much on this a little bit, because I've gone through a lot of energy audits in the Philippines, and I've seen a lot of white fillers. Okay. And the reason why they have white fillers, because um, they're not doing some effective blowdown. Okay. Now, what's an effective what does the blowdown do? Because as we all know, the only thing that evaporates in when you expose something to the sun is only water. Okay, so when you put in water into a cooling tower by the makeup water line, and it has a certain TDS, or conductivity, going to the basin of the cooling tower. And when you consistently going in and out of the building to your chillers, constant heat exchange, at some point there will be accumulated salt inside your basin, or sometimes it gets it coats the cooling water lines. Okay, so there's gonna the diameter of the cooling water pipes becomes smaller because of that salt. Okay, now how do we treat that? And it's gonna be two ways to treat it, and that is through um, um, anti-scalants, and of course the blowdown control using a conductivity controller. Okay, so these two considerations need to be very much observed. Okay, when we think that we are saving water because you're not putting in makeup water, you're not doing some blowdown, it might impact your pumps, for your cooling water pumps, because in the long run, you won't even know that there's already accumulated salts inside your pipeline. Okay, and the part also of the cooling water treatment, aside from the anti-scale, are the biocides, which can also make your cooling water pipeline small as well. So the combination of these two might make your system inefficient. Okay, and when you have accumulated salts into your cooling water pipeline, then as you imagine, when you get into the condenser barrel of your chiller, for example, the heat exchange between the air or the heat exchange, not air, sorry, the condenser barrel, the heat exchange between the refrigerant and the water will not be as effective before because of um, some scale that's already deposited in your pipeline. Thus, that's the essentiality of having a blowdown. Because when you make up water, you remove water, you somehow flush out the salts to the drain. Okay, but there are also some ways that people treat it by side stream filtration. So they somehow put a sand filter to the cooling water supply and cooling water return so that they will be able to capture the salt and have it captured in the sand filters and discharge it during backwashing. But that is typically applicable or more practical for district cooling system, very large systems, in order to have an efficient cooling water going around the chilled water air conditioning system. But for areas like malls, like some 1,000 to 2,000 TR systems, then at least a blowdown will be enough. And because we all know that we are quite sensitive about capex and opex, so we need to see that balance on how things are. Okay. Now, if you look at this diagram here, so you also have a point of measurement for how cooling towers are operated, and basically we all know about the approach, particularly facilities engineers. You just have to maintain the right approach, and of course the the cold water coming out of the cooling tower will never be same as the ambient air. So there will be times in the year where the ambient air will be just so how would I say, dense. Okay, so your cooling tower can only cool your water some 2 degrees below, two degrees above that ambient air temperature. Okay, so that's a thing that we need to also look into. Now, also for the cooling towers, the energy efficiency measure that we can always see here is basically you have an automated blowdown. Okay, because when you automate your blowdown, you have a set conductivity parameter, and then when you reach that parameter, you blow down, as compared to others who has a fixed blowdown. You're discharging water continuously. Well, it won't be the cooling tower that's gonna have a high energy consumption, but your plumbing, their water supply pumps will have to work additionally hard because they have to give makeup water to the cooling tower. Okay, and another thing is you can have a VSD control for your fans, so you could always could also be controlled by the approach or the ambient air temperature. So the right rotation of the fan will suck in the right air going to the cooling towers, and this will somehow give you savings as well. Okay, so that's I think one of some of the energy efficiency measures that could be applied here. Okay, all right. So
Sir, pwede
there's
magtanong?
also about
Sir Leo, pwede
yes,
magtanong po? Sir.
sure, Prof.
Sir,
Prof.
going back to the slide of blow down that you are discussing a while ago.
Yep, yep.
How
Mhm.
often, or how do we know that we have to to implement na yung blow down? Meron po bang yung ideal na time, like months ganon, or may level
No,
na
no, no. Actually, ano eh, hindi ideal yung you blow down every month or every so time. It's the best is real time.
real time,
Okay,
like
real time. You put a controller. Okay, and
okay,
that controller, yeah, that controller has a conductivity setting. Okay, conductivity is the measure of salts in the base in the system. Okay, so when the cycle goes round and round, the cooling water goes into the system. At some point, you'll have a conductivity so high that you have to replace your water already. But it's not ideal. Well, it can be done that you do batch blowdown, but of course, the problem here is the salt will start to accumulate slowly in your fillers. And when that accumulates, fine, after some time, mapapalitan yung tubig. But during that time, for example, 2 weeks, every 2 weeks ka magpapalit ng tubig sa basin, so may 2 weeks ka nag-accumulate ng ng salt dun sa fillers mo. Okay? And when you have salt accumulating in the fillers, of course, yung daloy ng tubig going to the to the for the heat exchange with the air, medyo ma-obstruct mo na siya.
Okay.
Yeah.
Pupunta condenser.
Yes,
Ano,
yes, yes.
ano po yung mga content ng mga sediments aside from salt po? May mga scale din ba yan or ano bang mga iba pang solid parts diyan?
Well, I don't know exactly the salt that the exact salts, no. Hindi naman siya yung parang table salt sa na nabibili natin. It's not that basta may chlorides yan eh. So there are many things that combines with chlorides like calcium or magnesium. So since it's many things that can get into the many salts that can get into the system. Okay, kasi nasa air siya. So anything in the air, especially if the air is polluted, so maraming pwede mag-combine dun sa water. Okay, and gets into your basin.
So ang bali real time na ating gauge is yung conductivity level po, parang ganon.
Conductivity or TDS, total dissolved solids.
Total dissolved solids. And then how does it affect yung system if hindi natin na maintain yung blowdown na paglilinis, and how does it affect yung energy consumption po?
Well, actually, yun yung risk eh. When you continuously operate na meron kang high level of salts, nag-accumulate yun sa pipes. Sa loob ng pipes, lumilit yung diameter mo. Pag lumilit yung diameter mo, konti na lang tubig na tataas yung pressure ng pumps mo.
Okay po.
Yun yung impact niya. Lalo na kung makarating na siya dun sa condenser barrel and chiller. Yung magsaswabbing ka na talaga. Brush mo na yung mga coils mo doon para matanggal yung accumulated salt.
So malaking effort din sa parang sa pump kasi may obstruction na sa sa daloy.
Correct.
Parang mas malaki yung pump na niya kailangan.
Correct. Oo. Okay. Yes, dun siya magkaka-impact.
Okay. Thank you.
Not to mention yung heat exchange, Yung heat exchange sa condensing side kasi meron kang layer of salt. Diba? So kung kumapal yung nagka-insulation yung yung condensing pipes mo.
Parang thickness, wall thickness.
Correct. Doon na makaka-impact din yun sa operations ng chiller.
Thank you po. Maraming salamat.
Okay, thank you. So ganun lang po, if you have any question, just raise your hand or just flag it up, then we can answer it real time. Okay. Now, going back, so we have air-cooled and water-cooled chilled water system. So medyo mako-compare pwede natin compare yan. So air-cooled has lower maintenance, it's a packaged system, it's a better low ambient operation as compared to water-cooled filter, which somehow have a greater energy efficiency and it's a longer equipment life, okay? Ang air-cooled chiller kasi, it's already a package, okay? This is very much applicable for those who wants to migrate from a split type installation, yung building na puno ng split type. Tapos na ang daming minsan i-maintain, so tas gusto nila i-centralize yung kind of system, pero hindi ready yung structure nila, air-cooled na lang yung the best kasi wala kang cooling tower na ilalagay, okay? Pero if you're gonna design it from scratch, might as well design it for water-cooled chillers because it has higher efficiency because the water has a better heat transfer capabilities compared to air. Okay? Tapos yung i-distribute mo dun sa both sa condensing side and sa chilled water side. Okay. Later on, I'll show you an actuary chart, which is usually our basis of efficiency of chilled water systems, and you will see na yung difference nilang dalawa in terms of efficiency. Okay. So, ito na pala. Yeah, here it is. Yeah. So, if the chiller capacity, ito yung ano yun, recommended capacity. So, if your chiller capacity is up to 500 tons, pwede ka pa mag-air cool na okay pa yung efficiency. But if you're gonna use a higher capacity up to 3,000 tons, you might as well use a water-cooled chillers. Okay, so ito na yung may cooling towers. Okay. All right. Now, let's even go deeper dun sa sa pinag-uusapan natin na vapor compression cycle. And this is where we have to consider na yung pressure enthalpy diagram. Okay? Kasi diyan muna makikita yung numerical values nung bawat process point ng air conditioning, no? So here we have a number 1, 2, 3, 4. So it's shown in the right, okay? So makikita nyo kung nasan yung 1. This one is over here 1, and this 2 is over here 3 and 4. Okay? So let me walk you through it again. Let me walk you through the pressure enthalpy diagram first. So basically, ito may makita ka. This region in the diagram is liquid. Okay, this region on the right here is vapor, and this region in the middle, inside the curve, the saturated light curve, is a liquid-gas combination. Okay, now how does these lines work? Okay, if you look at the isothermal line, okay, so dito makikita nyo, pag ang refrigerant is still liquid. Okay, for example, this is what the 20-degree line of a R134A refrigerant. It goes from here at a higher pressure, but if you lower the pressure, it will yung liquid niya will reach the saturated water line, and when it reaches the saturated water line, it will travel horizontally. Okay, dito na yung liquid gas. Okay, so nagto-turn na siya into gas. Okay, and when it reaches here, okay, sa saturated vapor line, it drops. Okay? Okay, so lahat ng refrigerant may yan yung flow niya depending on the temperature of the refrigerant. Okay? Now so bawat refrigerant has its own pressure enthalpy diagram. Ito R134A, which is typically used for chillers. Pero meron din yung R410, R20, R32, okay? So may kanya-kanya silang pressure enthalpy diagram. Okay? So again, parang lang yung walkthrough ko sa inyo kanina. So from the evaporator, so ito yung 1, then it goes here, compressor. So makikita nyo from the saturated vapor line, pupunta siya dito sa higher level, okay, so this is 2 here, okay, and ito yung 40 degrees Celsius, and pag pinadaan mo sa condenser, it will go here, magkakaroon siya ng heat rejection, so yung heat rejection niya will go to this 3, and then it drops here, ito pababa na lang to, and then it goes back to 4, okay, and then it repeats the cycle, okay, and here nga pala sa ilalim, you have 10%, 20%, 30%, 40%. That is the how much liquid is in the refrigerant before it reaches here in the saturated line. But actually, in reality, this point here, point 1 usually is operated here. Kasi dito kasi may risk na magkaroon ng liquid eh. Pag may liquid kasi, you cannot put it inside the compressor, masisira yung compressor. So normally, they superheat it a little bit more so that when you enter the compressor, hindi mapuputukan yung compressor kasi purely vapor siya going inside. Okay? Now, you can see here in the right is are some equations, okay, which is very useful when you do a review of your vapor compression cycles or air conditioning cycles, and this one can be used also for computation of the efficiency. Okay, mind you that the kilowatt here, okay, And it's usually the typical mistake na nami-mistake siya ito na electrical. Okay? Kasi meron kilowatt thermal and meron din kilowatt electrical. So we always have to be clear about that. Okay? Now, likewise, yung chart natin kanina, ito kung mapapansin nyo, ito in-over niya na ito, nag-superheat na siya, di ba? Yung kanina is the, paano mo back? Yung kanina is, di ba, nandito siya sa saturated line. Ito naman bago is nasa ano na siya. Ito na yung makatotohanan na nangyayari sa system. Okay? So, yung number one niya, dito na sa vapor region. Okay? Now, let me define to you, let me discuss to each of the equation. Okay, so Q evap is the measure from point H1 and H4. So H4 here, ito may enthalpy sa ilalim. Okay, minus the here, may enthalpy rin siya sa ilalim. Okay, multiply the refrigerant flow rate. So that is your refrigerating effect. Okay, so basically that is the cooling that is being produced by your air conditioning unit or your chiller. Okay, then you measure niya. Now, nag-input tayo ng power dun sa compressor. Okay, so meron siyang input power and that is ito yung H2 naman minus H3. H2 minus sorry, ito pala yan. Work compressor is ito yan. H2 minus H1 ito, compressor work. Okay? Ito yan. Okay? And cool condenser is measured here likewise with the refrigerant flow rate which is H2 minus H3. Okay? So as you can see here, ito yung kanyang mga equation. So you have the enthalpy here at the bottom. If you know, you have the refrigerant flow rate and you can practically produce the heat balance diagram using this chart. Okay? Now let's make it more real, no? Kasi paano ba natin on site, for example, you go to let's talk about the split type unit. Okay? Split type unit, lagyan mo ng pressure manifold and makukuha mo yung high pressure niya and low pressure. Okay? So you have two pressures already. And then, pag ma-plot mo yan dito sa pressure enthalpy diagram, so you have already two pressures, and then you get also the temperature using an infrared gun. You will be able to get the temperatures at these 4 points. Okay, and when you get, papaplot mo na siya. And you can already do the calculations using these heat balance equations. Okay, let me see, para may example naman yata ako dito. Anyway, before we go to the example, okay, let me expound again more on the refrigerants. Okay, so as I was discussing about refrigerants, each has its own pressure enthalpy diagram. Okay, and that's where we can design what is the best refrigerant for a system. Okay, now what are your qualifications in selecting a refrigerant? Okay, right now, more of the things that we consider in selecting refrigerant is more of environmental in nature. We now look at ozone depleting potential and global warming potential. Okay, and typically ito na yung nagko-control and what refrigerant is. What refrigerant will we be using? Hindi na nasa kamay ng consumers yan. Is usually the standard being issued ang nagdi-dictate na dyan, no? For example, if we're gonna compare it with water, as in would you believe water is also refrigerant, R718. ODP niya is 0, GWP niya is 0, ammonia is 0 and 0, carbon dioxide 0 and 1. Okay, but if we go into the typical refrigerant, so makikita nyo dito yung lumang R22, ang ODP niya is 0.034, ang global warming potential niya dito is 1,900. So medyo mataas yung global warming potential niya, tapos meron pa siyang ODP. Now, As we all know, naka-phase out na yung R22, so we shifted to R410. We have a zero ODP. Okay? Kasi ito yung ito yung priority nun eh. Save the ozone layer noon eh. Okay? Pero meron siyang risk with global warming potential. Okay? So, so far, wala pa tayong nakikitang kapalit for R410. And a very good candidate is ammonia. 0-0 siya. Pero alam naman natin ang safety risk ng ammonia. Okay? Medyo sobrang foul smelling. It can even cause nauseous pag nagkaroon ng leak. Okay? So ngayon nasa R410 tayo, pero meron next na meron amendment ng Montreal Protocol or na dati nag-attend lang sa ODP, ngayon i-consider yung GWP. Okay? And pero matagal pa yan. It's being the developed refrigerants are still being tested. Okay? Okay. Ito na example na pinag-uusapan natin. Okay. So, for example, we put a manifold and lumalabas yung high zone pressure niya is 2.5 bars and yung condensing pressure niya is 10 bars. Okay? Tapos makukuha natin yung compressor inlet niya via thermal gun, 5 degrees. Okay? Tapos yung compressor outlet niya is 66 degrees and then yung condenser outlet niya is at 34 degrees. Okay? Dito. So basically, mapaplat mo na tong refrigerant flow mo. Alright? Pero before that, make sure na tama yung chart mo. Okay? Kasi ito R1348 to. Baka pang ibang refrigerant yung ginagamit mo. Chart, hindi tatama yan. Okay? So here's, I think mali yung nabanggit ko. The high zone pressure is 1 megapascal pala, sorry. And the lower pressure is 250 kilopascals. Tas kaya nabasa kaya na-plot tong lines na to. Okay. Now, when you get this data, okay, makikita mo na makukuha mo yung mga parameters, lalo yung mga enthalpy niya. Okay? This is the point 3 and 4 is basically has the same enthalpy, so dito ka lang sa 250. Ilista mo lang lahat yan. Temperature at the condenser is 40 degrees. Temperature at the evaporator is -5 degrees Celsius. H1 is 410 kilojoules per kilogram, then H2 is 450 kilojoules per kilogram, and H3, H4 is 250. So na-plot na siya dito sa chart. Okay? Now, if you check the compressor, it has a data sheet. Pasasabihin mo yung flow rate niya is 12 kilogram per second. So you can basically compute all of these items. So you have a cooling capacity of 1,920 kilowatts based on this data. Compressor is 480 kilowatts. And the heat rejected, the condenser is 2,440 kilowatts. And from here, you can already compute for the efficiency. What is the COP? So 1,920 over 480, ang result niya is 4. And 4 is a relatively good COP. Okay, coefficient of performance. So you have now the result of your COP. Pero mind you, this 12 kilogram per second is based on a data sheet. Okay, so kung bang assumption nito is bago yung compressor. Okay, kung lumang compressor, mas maganda meron naman ultrasonic na pang vapor para makuha yung actual na refrigerant flow rate. Okay. Hence, gamitin na lang natin yung nasa datasheet ng compressor. Okay? So, let's talk about efficiency. So, the COP is ito nga yung kilowatt over kilowatt. Okay? And it can be converted to chiller efficiency na kilowatt per ton. Okay? So, ito yung conversion niya. Okay? So, for a COP of 4, okay, ang chiller efficiency niya is around 0.88 kilowatt per TR. Okay? So you can compare it now to the no to this chart. Okay, so kung 0.8 siya, it's more or less here at the good range. Okay. Pero mind you that this chart nga pala is includes chillers, condensers pumps, and tower fans. Okay. So yung 0.88 here could be somehow more in the actual kasi meron ka pang ibang loads na kailangan i-consider. Okay, the pumps, the power consumed by the cooling towers. So may papasok mo pa siya dito. Okay? And it's a mandated by law that we need to show the seller of the appliances need to show the energy efficiency ratio of the equipment. Okay? So, ang energy efficiency ratio, ang pagkakaiba niya, yung numerator niya is BTU per hour, yung numerator niya is power input in watts. Okay? And these are calculated by the manufacturers based on these parameters. Okay? Baka kasi sa actual yung kung nag-audit kayo tapos ko-compare nyo sa energy label pero ang ambient temperature mo naman is 37 tapos ang indoor mo is is lower, okay, so hindi magma-match. So you need to compare it apple to apple kung iyan mo sa energy label, kung sa energy audit process mo gagamitin to. Pero for selecting an air conditioning when you're gonna buy, magandang basihan to because they are tested based on these conditions. And there's also a IPLV, integrated part load value, and this is a way to be able to compute for the efficiency of a chiller. Okay, so it is based on this 12%, 45%, 42%, and 1% proportion of the load. Kasi hindi mo pwedeng gamitin yung tipong, kung for example, for a 1,000 ton chiller, okay, hindi mo pwedeng diretso yung gamitin 1,000 PR because in real time, you only use 1,000 tons 1% of the time. Okay? Tapos kung 1,022 kung 250 tons, yung 1/4 of the time is only 12%. But the bulk is between here 50% to 75% load. Okay? So I don't know how they deciphered this. I think they had an extensive study to be able to come up with this formula. So they were able to do this formula. IPLV is equal to this equation. Okay? And this is done in the manufacturing plant of the chiller manufacturer. Okay? So dito natin na-test to. Okay? Okay, some energy conversion. So there's power per ton, COP, and energy efficiency ratio. Pero the best na ginagamit ko lagi dito is the kilowatt per ton for chillers, and the COP is used for usually refrigerators and smaller capacity air conditioning units. Ito naman ER is used for energy labeling ng mga binibentang air conditioning units. Okay, so this was the thing that I've discussed to you earlier. Okay, so it can all be converted anyway from one point to another. Okay, what part of the HVAC system do you think are produced for energy efficiency? Okay, let me discuss that further. So, there's a rule of thumb, okay? 1 ton of refrigeration in a centralized air conditioning plant requires approximately 1.25 kilowatts of power, okay? So, kumbaga, at least you have that value in mind when you do your energy audit, okay? And at least you can somehow tell that when you measure, kailangan nandito ka lang sa range na nasa more or less 1.25 kilowatts ka to produce 1 tower of cooling. Okay? So this is on the basis of roof not exposed to sun and not too much glass areas in the walls. Okay? So may pre-qualification to be able to use this factor. Okay, this 1 PR is sufficient for office space of 18 to 22.5 square meters or 12 to 14 seats in a theater. And for example, for an office space approximately 1,850 square meter or a theater of 1,250 seating capacity, you need an AC load of around 100 PR, and more or less you'll have a power requirement of 125 kilowatts to produce that cooling. So this shows that the power consumption is sizable and there is substantial need to minimize it. Okay. Further, the cost of air conditioning constitutes 60% of the cost of the power of a building to power a building. Hence, the need to cut cooling loads to minimize the size of the plant. Okay. Okay. So here's a typical breakdown of air conditioning. So as you can see here, okay, 39% is HVAC. Okay, and 25% is is the others. Lighting is 9%. Then 1% is this is I think the domestic water, and 22% is equipment. This could be elevators or equipment in a room. Okay, so this is a typical HVAC load. Sometimes the HVAC can even go up to 60%, okay, of your energy profile pie. So at least pag may ganito ka, you'll know where to focus in finding energy efficiency measures. Okay. So there are a number of key end uses in HVAC systems. Okay. The bar graph in figure 2 shows a typical end use breakdown. Okay. So fans for air circulation and ventilation of 30 for around 34%. And these fans, baka inisip nyo lang yung, yung fan ng air conditioning. But if you include yung ventilation, yan, tataas siya sa 34%. Okay, kasi HVAC na tayo eh. And the cooling, yan yung para sa cooling is basically for the AHUs, so fan coil units, and of course the compressors and so on and so forth. So that goes into 27%. Okay. And heating most frequently of the energy use of boilers for the production of hot water. Okay. And but also the use of electric heaters for zonal reheat accounts to 17%. And of course the pumps, the 60%, cooling towers 6%. Okay, so ito yung typical HVAC contribution. Okay. Now, here are sample. Actually, these are real results of our energy audits. As you can see, dito sa Pilipinas, rather there in the Philippines, you will see that HVAC is really around 69 to 71%. Okay. But this can go as low sana as 60% if we're gonna optimize the system. Okay. And for hotels, malaki rin yun sa lighting. Okay. Malaki din yun sa hot water. And of course, in lifts, mas marami rin silang miscellaneous loads. Usually sa sa kitchen, sa restaurants, na marami silang miscellaneous loads. And sa Pilipinas, there's no boiler already. May konting boiler sa few hotels sa Pilipinas. Pero that is more on for laundry use. Okay? Kasi no, typically the hot water generation is using heat pumps or localized heaters in each of the CRs. So ito yung typical hotel distribution ng energy use. So for office buildings, and then malaki ang HVAC. Okay, then there's also wastewater, and there's also ventilation, and there's this lighting, and of course the lifts. Okay. All right. So that ends our P.4.3.1. Okay. So the next topic will be T.3.2, which is mechanical systems for air conditioning and ventilation systems. Before I move into this topic, is there any questions that wants to be raised by anybody in the group? Okay. Anyway, just list your questions or just put it in the chat box, and we could discuss it later on. Okay. And time check lang tayo. What time is it right now? It's 1:41. Okay. So moving on, okay, let's discuss mechanical systems and air conditioning ventilation systems. Okay, if you're gonna design an HVAC system,